Sonja Barkhofen, and she's going to talk to us about quantum walks in time. And she's from the University of Paderborn in Germany.
Thank you very much. Hello, everybody. Yeah, I'm Sonja Barkhofen.
Sonja, higher.
Still not working?
Yeah, as high as you can go on the shirt. Yeah, perfect.
Like this?
Perfect.
Can you hear me?
Better.
Excellent. Yeah, I'm a postdoc in Christine Silberholm's group in Paderborn. And since Christina herself cannot come, so lucky me, I'm here to represent our group. And yeah, attending here this beautiful workshop. And so thank you very much to the organizer and to the local heroes for having us here and taking care of us. Yeah, so in my talk I will present a couple of experiments that we did in the group in the last years, and that's why we have such a long list of authors and people who contributed to the talk. And so it was, these experiments were partially performed in Erlangen, where Christina was before, and then the new ones in Paderborn. And that's a collaboration with our theoretical friends from Prague. So it's, for example, Ligo Yax and Autography and many people contributing to that. So I divide my talk mainly in 3 parts. So we have first experiments on quantum walks in 1 dimension. Then I explain to you how we expanded the setup to a 2nd dimension. And the third is experiments on quantum walks and percolation graph, which has some relations to both of those topics. So let me start with quantum walks in 1D and a brief introduction. So we already have seen many pictures, many talks on quantum walks, but let me just go through it quickly. So we have our walker here on this 1-dimensional graph. He has no idea where to go, so he just tosses a coin and jumps then either to the right or to the left. And this can be also implemented in those Golden board, and this gives me the possibility to show these videos that took quite some time to make. And yeah, so after several runs of such an experiment, you end up with this famous binomial distribution, and the variance of the distribution spreads with the number of steps, so it's a diffusive spread. And this is of course totally different if you're in a quantum walk, and I will talk only about discrete quantum walks. So here our Hilbert space is divided into subspaces, so we have the coin space, the internal space, that can be a spin, or we will use the polarization, so any 2-level system, and of course then the position space. And since it's a quantum walk, we can of course have those superpositions of spatial distribution. And one way to represent that would be such a classical Golden board with this beam split arrangement, where you can immediately see here these interferences, and these constructive and destructive interferences then gives rise to a completely different outcome distribution that may look like this. So you have these pronounced peaks here, and of course the specific shape of this distribution then depends on the initial state on the coin. And you see that the spread of this distribution is much faster, so it goes with n squared. So we have a ballistic spread, and yeah, it differs very strongly from this classical distribution here. Just as a short repetition, so this classical random walk is of course a very famous model which can be applied in all fields of physics, and I just learned that even stock market dynamics are modeled using these quantum walks, and also its quantum analog has very many applications. I just couldn't find a comparable
there's no quantum stock market.
No, there's no quantum stock market, so I couldn't find a point to that. But maybe in the future we were talking lots about applications, so we will see. So how do we model our discrete time quantum walk? So assume we have such a walker here in this superposition of vertically and horizontally polarized light, and then we apply a step operator which then moves the one part, one position to the up or to the right, and the other part to the down. And this is then typically written like that, so it tests what is in H polarization and will shift it to X plus 1, what is in V polarization, shift it to X minus 1, or the other way around, it doesn't matter. It's just conventional thing. But to come to such a superposition, for example, from an input state which is only vertically polarized, you need a coin operator that then rotates the polarization into such a superposition. And the application of step and coin operator then on such an initial state makes up one step in our unitary quantum walk evolution. And if we want to then have more and more steps, we just add them up and end up with such a pyramid or cascade of coin and step operators, so that the n times application of coin and step on our initial state then gives us the final outcome outcome state of our quantum walk. And since I'm going to present to you results on that in a second, I can already rewrite that, so it is possible that the coin operator may change from step to step and even from position to position, so that we have a time-dependent dynamic coin operation, which we will then realize in our experiment. So yeah, there are many experiments, many different platforms, so we already saw several of them, these beautiful pictures here by Alberta and many more, so many different implementations. And each and every of them has its own advantages, maybe disadvantages, challenges, chances. And of course, I'd like to convince you in the next few minutes of the advantages of the system that we are using and that we are convinced of. And this is such a time multiplex quantum walk. So we have a loop architecture of some free space path and some fibers here using polarizing beam splitter and standard linear elements. And the coin state, as I said, is represented by horizontal and vertical polarization, since this can be manipulated very easily, so that we can, just by having some half-wave plates here, prepare any arbitrary initial coin state. And at this point, I have to admit that we are not working with single photons and not working with two photons, so we use V-coherent laser pulses, or one V-coherent laser pulse as a walker, because this is just analog to the dynamics of a single photon. But since there are, of course, several photons included in the laser pulse, so I think it still fits in the context of this workshop, and we have an interferometer here, so it's perfectly fine, I hope. So let's assume now we have our walker here in this prepared coin state coming into the setup. Then we have like half-wave plates here, or maybe electro-optic modulators that represent then the coin operator, and then So, according to its polarization, the walker is routed through these single mode fibers here, which have different lengths. So you will see that they will introduce a time delay between the different components of the pulse, and then they will recombine here at the second beam splitter, and we close the loop so that these two pulses then will enter again the setup. And but before they will do, we couple out a small part of the intensity, send it to our avalanche photodiodes, so we have a detection resolving, polarization resolving detection unit here. So how does it look in detail? So the principle of the time multiplexing, well, first of all, of course, we have the coin operation, for example, such a half-wave plate, which we can then rotate to any angle that we want to, which then rotates the polarization so that we have these two parts here which travel through the fibers of different length. And now this relative shift in time then of course corresponds to our step in position space. So every time bin then uniquely represents a position in space. And if we now look at the second step, the second round trip, So we feed in these 2 pulses again into the setup and end up then with 4 pulses, but these inner 2 will interfere because they have traveled exactly the same path. So one just first the short fiber and then the longer one, and the second one, of course, the other way around. So they have seen exactly the same components, and this is what makes our setup very stable against decoherences or any dephasing effects of the devices. And of course we can then fed in these 3 pulses again and again and again, so that we have the quantum walk evolution over several steps. And this is one result that we obtained. It's a Hadamard coin, so which is a fair superposition of horizontal and vertical line, and no extra phases, so there was no EOM included. And we can see here this nice result over 28 steps, which agrees very nicely here with the theory within the error bars for the quantum walk. And you can clearly see that it deviates strongly from the classical prediction. And just as an information, if you want to realize a 28-step walk in such a beam splitter cascade, you will need 406 beam splitters and 29 detectors for these 29 positions. And our setup is, compared to that, very resource efficient, since we have just a constant number of devices and just 2 detectors. And this is not step dependent then. And since they are always traveling the same path, we have this setup provides very large homogeneity over the step number. And so this confirms the very high degree of coherence that this platform that we're using provides. As I already said, we have these electro-optic modulators, so we are able to switch in time the certain positions, for example, like this, so that we have different phases here at all positions in all steps. So we have these fast fluctuations of the coin. So we used again a half-wave plate here with a fixed rotation, and then this extra phase here randomly applied by the EOM. And as we've already seen in several other talks, that this destroys then, of course, the decoherence of our walker and brings us back to the classical distribution. Here again in the log plot, where you can see this nice parabolic shape, which is the signature of the binomial distribution. So by this we are able to suppress the interferences and come back to the diffusive spread. Another situation that we investigated is the static disorder. So phase changes from position to position, but it's constant over time. And here you can see again this peak distribution with the highest intensity here in the middle, but the log plot reveals that we have now not this parabolic shape, but a clear exponential decay. So a stagnation of the spread, which is then the signature for the Anderson localization. Of course, we have averaged over various distribution and various realization of the noise to get these results here. And so this is then a clear signature that this is really a wave interference effect that we see here, this exponential decay. And since we are quite flexible with the setup, we can tune the strength of disorder just by choosing the interval out of which we sample this phase here. So just by choosing this phi max here, I hope you can read it. So if you have a look here again at the situation where we have fast fluctuating noise, we can just by increasing the size of the interval have a smooth transition from the quantum to the classical walk. So we are able to tune that very precise. And the same is, of course, then possible for the second situation where we see this Anderson localization. And if we then plot the width of the distribution, or the variance of the distribution over the noise strength, we can see that here for the red case, it smoothly converges against this classical variance here, this classical limit for the diffusive spread, but that for the case of Anderson localization, we clearly see that we can go below that so that we can prove that it's really a localization. So up till now, all these experiments were performed in one dimension. It's a one-dimensional walk, and we could vary the coin statically or dynamically. But now, of course, you would like to be even more flexible and would like to add a second dimension so that you would have a walker running or jumping on this two-dimensional grid where you have then even more paths that interfere here at a certain outcome distribution. So how would you model that? So let me start with a short overview over the theory. So now we need a wave function where the basis then includes, of course, two spatial components, x1, x2, and also the coin space must now be four-dimensional, so for regulating the movement in both directions, so that we have a four-dimensional coin operator, and then our step operator consists of first a shift in x1 and then a second shift in xy direction, so that after a step we can end up here at these positions. This is completely analog to the description of two particles in a one-dimensional quantum walk. So you can interpret the x1 and x2 directions here as the position of walker 1 and walker 2, or particle 1, particle 2. They both have their coin state, and so again we have a four-dimensional coin operator, and the step operator then can be interpreted as first a shift for particle 1 and a shift for particle 2. So these two situations are completely equivalent in their mathematical description. And this is very nice for us because I said we are not at the point that we can include several walkers in our experiment, but we were able to increase the dimensions, and by investigating the 2D walk, we can now investigate two particle dynamics with classical laser pulses.
So you assume particle 1 and particle 2 interact in some way, right? Or they can't be just independently working?
We can tune the interaction with this electro-optic modulator. I will show in a second. But first I start with the description of how we implement that in the experiment. So this is again our 1D loop, and you can immediately see that we have two empty pores here of this beam splitter. So this is of course a waste of resources. So we connected them so that we now have two free space paths here, and yeah, of course our fibers. And now let's see, and included of course some more half-wave plates and more measuring units. So let's see what a pulse entering the setup is doing now. So of course, or at first he will travel as before through these fibers here of different length, and will then see the two components, the vertical and the horizontal, will then see a large time delay compared to each other. So no, this is about the coin states. Yeah, okay, now it's the step operation. So we have this fiber delay here, which then defines the spread in x2 in a vertical direction here. And then the walker is splitted again here at the second beam splitter, so that parts of that traveling through the shorter path and some parts are traveling through the longer paths, which gives us another time delay, which then represents the horizontal step. So that after one round trip here, we end up, or we can again encode the different arrival times of our walker as these positions in time here. And that we really have a four-dimensional coin space is defined by these two detection units. So again, we have the two polarization degree of freedom, and then but two spatial degree of freedom here, so that we have access to all 4 degrees of freedom. Yeah, so this detection is again polarization resolving, as I said, but again it's also time resolving, since we couple out in every round trip, so we have the access to the full evolution of our walker. So this is how the timings or the time separation then might look like. So we have different separation of different time. For example, here that small separation, which corresponds to the x1 direction, a larger separation, which corresponds then to a shift in x2 dimension, and of course the very large separation, which is our step separation. So you can see that every pulse can uniquely identify, or that uniquely corresponds to one position on our grid here. And of course this becomes more complicated as further the walk evolves, because we have more splittings and more pulses, but still the unique correspondence here remains. So yeah, that our walk spreads now on this two-dimensional grid. And we have to extract the data now from our 4 APDs, and this is how it might look like for step 6. So you can see here the larger separation between these groups of pulses and this very small separation, only a few nanoseconds, for yeah, here this small x1 separation. So from this data you can then extract the full 2D information, positional information of the walker. Yeah, so what are now the coin operations that we can access? So this is again a repetition of the one-dimensional quantum walk, where we, for example, have a Hadamard walk here connecting the vertical and the horizontal mode. But now we add these extra modes here for the second dimension. So we have this 4-dimensional coin, and again this half-wave plate then can be written as this block here. But then we include some more half-wave plates, for example this one, mixing the two modes coming out of this second path here, and then another half-wave plate mixing these modes, and a fourth one mixing, for example, here the H mode and this V mode here. And additionally, we have this EOM, which gives us one position or time-dependent phase here on one of those components. So if you add it up, or if you multiply all those components, so these are the coins that we can access. I have to admit that this is not the full 4D coin space, so we cannot access all coin operators, but we have connected or can mix up all these paths. So we have an entanglement of all paths, so our coin operator is not separable in only a 2D coin. So what are now interesting situations that we could observe? So for example, here the walker on a 2D grid, and we could, for example, switch on the EOM, so give an extra phase on these diagonal positions here. And speaking in the two-walker picture, this would mean that at those positions where the walker meets, so for example x1, walker x1 at position 1, walker x2 at position 1, they have an interaction because there's an extra phase. And since the EOM is programmable and flexible, we can imagine other situations that, for example, on the diagonal we just give a random phase, or only on every second spot we give this phase. So there's a large variety of situations one can study now in this system. So this is one of them, the most boring one, of course. So both particles or in both directions we just apply a Hadamard coin, so there's no connections between these two walkers. And so we see exactly what we would expect, that we have a situation where these particles are distinguishable, there's no interaction, and we have two separable distribution in theory, and of course a very nice agreement with the experiment. So that's just a check if everything is aligned properly and we understand the system. So let's go to the more interesting situation where we apply a strong interaction when the two walkers are sitting on the same spot, so when they are meeting each other, and just the Hadamard for all other positions. And here you can see in theory and in the experiment as well, the strong pronunciation of the diagonal And this means that the two walker then tend to stick together, so they build kind of found state. And again, let me stress that we have this very nice agreement between experiment and theory, so that even the structure of this state is reproduced very nicely in the experiment. So this is an example where we really could use our quantum walk as a simulator for these strong interacting particles. And then there were, of course, these other situations where we applied here, for example, a random phase on the diagonal, and you see that the tendency to bound together is a little bit weaker, but still the diagonal is pronounced more than these off-diagonal elements. Or for this alternating interaction with just every second spot on the diagonal, we switch on the interaction. We see still the diagonal, but now here this extremal peaks are pronounced most. So, but in all of those cases, we have this very nice agreement between theory and experiment, and perform the quantum walk up to 6 steps here. So this brings me to a kind of intermediate conclusion, because those experiments were performed quite a while ago. So let me just repeat that I've shown to you that we were able to implement the one-dimensional coin quantum walk in this time multiplexing setup, where we can apply a coin which may fluctuate in time or in space or both, with which we could then reproduce the classical dynamic or even show Anderson localization. And the second part was the two-dimensional quantum walk, which is equivalent to two particles on a 1D walk, where we could study this interaction and found these bound states. And this brings me then to the second topic. Those are quite recent experiments we performed last year or this year, quantum walks on percolation graphs. And let me for that start with a short introduction. So we've already seen this picture and heard lots about quantum transport in those complex molecules. So this is just a small selection of publication, and we've already seen beautiful experiments to that. But we think this is quite too hard to study for us. So let us check what ingredients we would need to model or to understand such a quantum transport. Of course, we need our quantum walker, quantum evolution. And this walk then will take place on a discrete network or graph. So here it's only two-dimensional anymore, so it's a little bit simpler. But since nature is just not ideal or not perfect, what might happen is that some of those links are missing. Or that even those perturbations here are not constant, but are fluctuating in time. Or even worse, that we don't know what the actual configuration of our network or molecule is, and we have just the probability information of those links being present or absent. And the question is, can coherences, these quantum coherences, be preserved in such a system, or destroys this randomness or this lack of information immediately the coherences in those systems? And there's a very nice paper by our collaborators in Prague and Hungary on coin quantum walks on percolation graphs, where they studied different systems which are similar to this example here. And so that was the motivation for us to identify a system that we could study in the experiment, and then may answer this question, how far or if coherences can be preserved.
You didn't mention direction in the original, that biological process would have directed work. Can you study including the directions of weighting?
Or
Sorry.
the direction of the...
It's just mapping from what you started with. That has clear direction. Sorry.
So this is just the motivation. So we are not able to study like this,
it's nice.
this molecule, and we have some ideas how to maybe include a direction of our links, but this is not what I will present here.
Sure. Yeah, just because it's really nice, you consider all the other possibilities, randomness and time dependence. but there is a fundamental process which drives the electrons, whatever excitations, towards one particular direction. Normally, that's what a biological process would be. But yeah, that's already very nice. I was just
honestly
wondering.
a very interesting direction to go, and we were discussing that already. And but this is, let's say, the first step on the way to understand like quantum transport in real biological system. So that's a toy system, what I will present here. So let's again go back to our walker with this classical coin, or in the coin, or in the quantum case here, this quantum coin represented by the block sphere. And now what can happen, so we are back in one dimension, so back in the simple case, that we have these gaps here, and that may change in time. And so now this walk is not described by this coin and step operator, which are time independent, but now it's the step operator that changes over time, because the step operation has the information in which direction it's allowed, or the walker is allowed to jump. And so this is in contrast to the situation I described before, where the step operation was constant and the coin was changing over time or over space. So again, our fluctuating graph, and the way we will represent it is that we use then the y direction to indicate which certain configuration we have at which step, because this might change. And the concrete system that we're interested in is a very simple, nice toy system. Just a walk over 3 sides, so reflecting boundary conditions here at the edges, and we want to simulate a link probability of 50%. And I can already tell you that we'll check, or we will test the coherence properties in the quantum coin, so in the polarization state of our walker. So how can we then do it? This is again a picture of our 2D setup, and now we want to vary the step operator. But this is, of course, not so easy, because the step, as I told you, is given here by this length difference of the 2 different fibers, and we cannot, of course, like plug and unplug these fibers in time. So we have to find another solution, and so we now use this setup in a different fashion. So for the 2D walk, the walker was using the paths simultaneously, with both free space path here, but now we force the walker to alternate between this path here and this path. And then we can use the EOM as a graph operator, so we have the walker doing a normal step operator, then passing the EOM, which can then do a graph operation, which I will explain in a second, and then do another standard step operation through this fiber here, and goes back where it started from. So in the way we use the electro-optic modulator now is that if we don't apply any voltage, we realize here this identity operation, which corresponds to a transmission, as I explain in a second. Or if we apply a voltage, then we have this operation here, which will correspond to a deflection. So H will turn to V and the other way around, including some phases and so on. So what's now the dynamic? Imagine we want to realize this state here, or this configuration here. So one link is there, the other one is absent, and this might change over time. And now we have this intermediate step here in between with the graph operation. So let's start with that part of the walker, for example, here from this position, that wants to jump to the left, which is allowed. So it first will travel through the corresponding fiber, will pass the EOM in this graph operation, and since this is an allowed transmission, we want to have a transmission operation, so we don't switch on the voltage, and the walker is just continuing its way in that direction. So it's performing 2 half steps to the left, and the link is there. So the interesting part is, of course, that part that wants to jump to the right and is not allowed. So first, it will jump to the right, because that's the corresponding fiber. But now we can switch on the EOM, change the polarization of the water, and it will then travel through the other fiber, so it will make half a step to the right, half a step to the left, so that finally it remains and it's on its original position, just in another polarization. And this is how we then break links, and since it's just a programming thing on the EOM, we can change that from step to step if we have like transmission here or transmission there. So that's just the reprogramming of the electro-optic modulator. But the price we have to pay, you've already seen them, is that we now need 2 round trips in the setup to perform 1 step on the quantum walk. Yeah, and this is how, for example, spatial distribution then looks like. So again, this is system that we want to simulate. Of course, we know which configurations are there and which are not, and that's why we have to average over all possible configurations where we have one link present, the other one absent, which is 2 possibilities per step, 6 steps, so it's 64 different patterns, 64 configurations. Would hardly be possible to do with waveguides, I guess. But for us, it's just reprogramming of the EOM, so we measured like all 64 different patterns and compare these outcome distributions with our theory, so that we can be sure that the system is aligned properly and that it's doing what it's doing. And then we average over all of these configurations to simulate this graph. And as I said, we are interested in the polarization state, so we trace out the spatial distribution. So for the pictures before, you typically space out the trace out, the coin degree of freedom. Here you trace out the position degree of freedom. We performed full tomography, so we not only measured 64 but 3 times 64 patterns, so that we have the Stokes parameter here. And from that we can reconstruct the density matrix of our state. And if you now want to investigate coherences, you should compare that to the totally mixed state where no coherences are left. So what we then calculated is the Hilbert-Schmidt distance, so I gave here the definition again, of our calculated state of the measured quantum walk to the totally mixed state. And this is then what we got here. So in the beginning, that's maybe the behavior you would expect. So we are very close to our to the totally mixed state. So the system is completely incoherent. But then you can see a revival of coherences, so moving away from the mixed state, which is a clear signature of non-Markovian behavior of our system, since we have this revival of coherences here. And you can see that the effect is very tiny, so this is the density matrix, and the coherence terms are here these off-diagonal elements, which are 0 here, and quite tiny here, but they are still measurable. And you can see that we have a very nice agreement here of our experimental data, the red curve, and the theory where we included some imperfections like losses or slightly detuned coin operators, so within the error bars we can really reproduce here this theory curve, and this shows qualitatively the same behavior than the theory for the ideal walk. Yeah, and this is work that we just submitted quite recently. Yeah, so this brings me to my final conclusion. So I have shown to you that we can do quantum walks with this time multiplexing setup in 1 and 2 dimensions. I've shown to you how we break links, so that we have a dynamical percolation graph by modification of the step operator, which needs then a large flexibility, stability, and homogeneity of our setup, so that we're able to average over these 64 configurations with this electro-optic modulator. And with this, we were able to really show this tiny effect of this revival of coherences with a high precision, where we tracked the time evolution of the walker and, of course, needed then full access to the polarization state. And since this is a very flexible platform. We have several ideas how to continue. So first of all, we would like, of course, to increase the number of steps over which we can track the evolution of the walker. And so there's one similar, completely fiber-integrated loop system where they use amplification, and as long as you're using coherent laser light, this would be one step to compensate for losses. And then we've already seen this picture here, this boson sampling proposal, where they use kind of similar loop setup, so maybe our platform can be adapted to do this. And a very nice thing would be, of course, to combine the features of our experiments, so the 2D grid with percolation, so that we maybe can realize graphs like this. So we've already seen that in your talk, so that we can study quantum walks on those exotic graphs like these star graphs. And this is the end of my talk. Thank you very much for your attention.
Thanks for the very nice talk. So, time for questions.
So it's really interesting that you expect to get up to 28 steps, and then you're using the EOM to get both site-dependent and time-dependent coin operations. Is that right?
Yeah,
Okay.
that was the first.
So the EOM works really well that way. You're able to get changes in phases during each step during the transit time of the light. It looks like it has a high demand for control during the different cycles, but maybe it's easy. I don't know.
Yeah, we were using two different EOMs. So the first for the first, the Anderson localization and this phase variations, use an integrated one. Those are typically very fast, but not that reliable in the phase you want to get. So that was okay for doing these random things. But here for the second case, it's true we need a higher position of these reflection switching. So that was another EOM, a free space EOM, a Pockels cell, where we then needed some time to understand it and to apply the correct voltage that we get a rotation and not more or less reflection rotation and not something in between. So so it needed some time to really get this precision of the switchings. And was that your question?
Yeah, that's exactly, you've answered it. And then in the plot, when you were showing the theory versus experiment, there was a discrepancy, of course. You know, it's normal. What is the significant experimental limitation that?
This plot here. So the difference between the red or the blue curve and here this ideal theory.
The red and the blue.
So we included some imperfections, or we were able to include some imperfections in the theory, like losses on the 4 different paths. But of course, you can never include all imperfections that you.
No, I'm just wondering what you think would dominate. So your loss is a major factor. That accounts for the orange to blue, correct? That's
true. So
okay. No, I'm just curious what if you included more in the theory, what would be the next thing you would include?
So we allowed for slight detuning of the coins, so that's not exactly a Hadamard coin, but a slight detuning of the half-wave plate, and then included that the EOM might not switch a complete reflection, but just 99% of the reflection. So these were the parameters we included here in this adaptive theory plot.
Any other questions, comments? Yeah.
As if I need the microphone.
But back to your question about directionality, I'm not an experimentalist, but typically when they want to break directional symmetry, they put Faraday rotators, right? So the photon goes this way and then is rotated by some amount, and then when it tries to go back, it finds the polarization is wrong, and so it's forced to go in one direction and not, it breaks the time reversal symmetry. So maybe somehow putting Faraday rotators would give you a directionality that you would need to mimic the Fenner, what is it, the Fenner-Matthew-Olson complex?
Sir?
The light
This
harvesting.
molecule.
Yeah, FMO?
Yeah.
Yeah. So I'm just thinking something like a Faraday rotator might be a simple linear element that could do something like that.
Yeah, I'm not sure how this translates to our time multiplexing scheme because
Right.
we have to reinterpret then the arrival times again at for position in our walk, and I'm not sure what happens if some pulses are then by chance traveling backwards in the setup. So I'm not sure how to.
The thing is that the Faraday is normally dumping the photons in the wrong way, not as opposed to reflecting them. So
What did you say, dumping?
yeah, I mean, what happens? They go into another mode, which is typically a free space mode. So
Right, but it doesn't have to be a free space mode. You could make it another mode in the graph, that's my point, and then sort of get a forward direction that way.
I don't know that you can do that.
I don't know either. That's why I asked.
Maybe some conservation.
You want to use
So I don't understand this directionality. Is this just the landscape of the Hamiltonian that makes some
Yeah,
local minima and the tunneling is guided in that direction?
yeah, that's right. It's a non-unitary process.
Just to understand.
They're asking questions, about things you didn't do.
When the
So
direction-
let them fight it out. You're off the hook. So.
Interesting discussions.
I guess the directionality is just a feature of the Hamiltonian, right?
So maybe a last comment from me?
I was curious too, and have no answers. But basically, if you do the walking, and currently, most 99% of the study are non-directed and no weighting, right? But in reality, the walking can be directed, and different direction can have a different amplitude.
Yeah, but what is the physical phenomena that leads in this bacteria?
But can we postpone this to after the session?
Yes.
Because
Some related to
Why is
Oh.
not?
yeah, so we'll thank Sonja again for the talk. And there is the last